Hello again. So this is ML103. This is Introduction to Generative AI. This is, I think, the longest lecture here, but it goes into a lot of details on GenAI. Okay, so what is generative AI? So generative AI, like we said before, is a subset of machine learning algorithms that generates new content. In a lot of predictive ML, the objective, the output of the model is pretty constrained. It in supervised learning, if you're classifying that it chooses one of those classes, it doesn't go outside of that. In regression, again, there's a range, it's a number. But so generative AI is able to create content that it hasn't seen, but from information that it has seen before. And it emerged in the public eye in November, I think it was 30 November 2022, when OpenAI launched ChatGPT for free. And before that, GenAI was really, it is a field that has been around for a while, but in 2022, it was put in the public eye, and the world has never been the same since. And so a lot of what we see, generative AI can create content in different modalities. So it could be in language, it could be text generation in language, it could be image generation, it could be in videos and audios. And so the inputs and outputs can vary widely. But the most success we've had has been in language. A lot of the really cool things are happening in language, and those are fueled by large language models, LLMs. So let me tell you a little bit more about those. So LLMs, as the name suggests, are large language models. And we'll see what large means. And they are sophisticated types of neural networks, right? We were just playing with neural nets. You should know by now that it's just another formula. It's a mathematical equation that's quite complex. And we played with the TensorFlow playground, which you can build your own neural net. You can decide how many hidden layers it has and how many neurons per layer and how they're connected. I don't think you can change how they're connected. I think it's a feed-forward neural net. But anyway, it's just another type of neural nets with a particular architecture. Large language models are characterized by their large number of parameters. They're often in the billions or trillions. And LLMs understand the probability distribution of words and sequences. If I have time at the end, I'll show you a visualizer of the transformer model, which is the heart of these things. And hopefully you'll be able to see what this means, the probability distribution of words in a sequence. The primary goal of an LLM is to predict the next word. It's kind of greedy in its way of working. It really is a next word predictor based on previous words, and it can capture both the syntax, which is the arrangement of words, and the semantics, which is the meaning of words. And LLMs have proven useful for a lot of things, including translations and natural language generation, speech tagging, information retrieval. There's a lot of different use cases which we're going to look into. And the way they work is they use self-supervised learning for pre-training, which removes the need for explicit labeling. And it's a really cool technique if you want to look under the hood, but this is out of scope for me. Example tasks that LLMs can accomplish. Well, we know they can read. Okay, so they have been super useful in things like proofreading, summarizing, analyzing content, classification. We know they can write, so they've been also used as stylistic polishing agents, answering questions, first draft generation, translation, code writing. And because they can read and write, then they can converse. That's actually not necessarily true. It's not because they can do these things. They've been fine-tuned to do that. But we see a lot of chatbots, a lot of natural language layers on top of knowledge bases. And so a lot of common uses, some of the common uses we see is, essay writing, summarization, translation, information retrieval, conversation assistance. image generators, coding tools. There's have been a proliferation of use cases for LLMs. Okay. Oops. Where am I? Okay, so possible issues with LLMs. Well, hallucination is one issue. Hallucination is when a model doesn't have the proper information, and so it comes up with a very reasonably sounding explanation. And because the objective function of an LLM is to optimize for next sequence prediction based on probabilities, it's not optimizing for accuracy, right? It's optimizing for sentences that sound reasonable, not sentences that are necessarily accurate. Okay, so that's a very important thing to know. And so it sounds like human sentences. The actual content and accuracy is beyond the scope of the LLM, right? It has seen information, and if it sees it enough, then the probabilities would reflect that, but it's not optimizing for accuracy in general. Okay, so that's called hallucination, is when it comes up with a response that sounds reasonable, but it's not. It made it up. Knowledge cutoffs. Models only know about data they've seen up to a point. So if a model was trained in 2024 and you say, well, who's the president that was voted in 2025? It does not know because it did not see that information. There's issues with context windows, or that's at least a property, is how much information can it take in or spit out? And that varies widely by models. There's issues with bias on toxicity. The model sees data from the internet, which of course, there's a lot of biases baked into data. And so the model sometimes reflects that. They're still not really great at structured or tabular data, and they're not really good at number processing, and we'll see why. There's a few issues where they're not necessarily great at, but they are very powerful and they do a lot of really cool things, and we'll see some of those things. Okay, so again, I'll go through terminology or glossary. Some of it might seem abstract. We're going to talk a lot about these things in details, but these are things we hear about. So again, we talked about artificial intelligence in one of the lectures. It's techniques that enable computers to mimic human behavior. ML, or machine learning, is a subset of that. So it is techniques that allow computers to learn without explicit programming. So they're mimicking the learning side of humans. Generative AI is a type of AI that allows computers to generate new content. We've seen all of this. Now, what is an LLM? It's a large language model. So it's an umbrella term for models specialized in language. What is a transformer? So the transformer is an algorithm or a neural network that revolutionizes GenAI and underlies LLM. So it's the heart of the LLM. It's the actual architecture that underlies this LLM. A prompt is the input to the model. It's the actual text that you're giving the model. That's the input. It's called a prompt. A token is a word or part of the word. It's the currency of an LLM. So the context windows that we talked about, how much it takes in or spits out, is it's the unit of measuring input and output size. Is a token. An embedding is a numerical representation of a non-numerical entity. So it's a projection into mathematical space, and we'll see why this is important. RAG, we hear a lot. This is a retrieval augmented generation. This is the use of an external knowledge base to augment the system. Again, I wanted to put them all here, but we're going to go into more detail. A foundational model is an ML model trained on vast data sets so that it could be applied across a wide range of use cases. So this is a very powerful model that somebody trained that you can use for a wide variety of tasks. So one of the things that people, I think, don't really realize is the size difference between GenAI models and predictive ML models. And as I said in some of the previous lectures, the bigger the model, the more capable of learning it is. It needs more data, but there's more tunable knobs and more information it can encode. Okay, and so I want to just give you an idea of the generative AI sizes. So MLs, like I said, are sized by the number of parameters. This tells you, this is a proxy for how big the model is. And it ranges from one parameter. So we've been playing with logistic regression, linear regression, sorry, with two parameters, ax plus b. It could be as small as y equals ax, right? This is a line that passes through the axes. I don't think there's any real use case for that, but you can imagine that that is the smallest possible equation, and they can go all the way to 2 terabytes of parameters. I think if the leaks are correct, I think GPTs are about 1.8, so I'm averaging about 2 trillion. So the predictive ML space is about millions of parameters, right? The biggest ML model that I had ever trained is like, I think, a 64,000 convolutional neural network, right? And so thousands and millions of parameters in the predictive ML space is quite powerful. The generative AI models are in the billions of trillions of parameters. So they're roughly 2 orders of magnitude greater, right? And this is the NLP Moore's law. And so every year model sizes increase by roughly 10x. So we can see that BERT and GPT, for example, BERT is about 340 million parameters here, and this is 2018. The GPT-3 was at 170, and now this is 2021, so it's quite out of date, but now we've reached the 1.82 trillion parameter mark. And I want to give you an estimate of what that means in terms of resources. So a single parameter in a model or a single number, when it's stored in the computer, on the computer, it's stored usually as a 32-bit float, right? And what that takes is about four bytes. And so if you've got a billion parameters, just as a ballpark, we've got 2 trillion, but let's say you've got a billion parameters, that's roughly about 4 gigabytes of RAM just for the parameters to load, right? But when you actually train the model, you need roughly about 20 times more space because of that whole cycle we talked about. So you've got your parameters, you're making predictions, you're calculating errors, you're updating parameters, and you're saving some metadata, and you've got activations, you've got gradients, you've got the optimizer, and so there's a lot of metadata that is saved across that process, and it takes about 20 times more space than the parameter size to train. And so if you've got a 1 billion parameter model, you need about 80 gigabytes of RAM to actually train this thing. And as you see, we were over the 1 billion parameter models a long time ago. These are this of course comes from the Coursera course, Andrew Ng's Coursera course, if you want to look at that reference. So imagine the requirements of about 1.8 trillion model, right? So these systems are very large, and they've put constraints on compute and data, and they've made parallelization and optimization, both at the hardware level and a software level, a must. So there's a lot of work in the GenAI space to optimize everything from compute to memory to processing to loading, everything. It's really forced us to really push optimizations to be able to better support these things. So this is a really cool slide that I've taken from a lecture that Yann Dubois, a doctoral candidate at Stanford, gave. This is on YouTube. You could see it in the reference section. I have a reference section, and it's if you Google Stanford CS 229 lecture, you should be able to find it. But anyway, these are not my estimates. These are Yann Dubois, but they're really cool to give you an estimate of, again, the resources required for training. And so he uses the example of Llama 3, which is about 400 billion parameters, large. And so it's exactly 405 billion. It's trained on data that's about 15.6 trillion tokens. The token per parameter ratio is about 40 tokens per parameter, which means that it is trained compute optimal. We didn't talk about this, but there is a paper that came out called the Chinchilla paper, which looked at, these are called scaling laws. This is information about how the performance relates performance and model relates to model size and resources it used in terms of various things we could look at. And in the paper, I think their estimate was that you need 20 times the number of tokens. So there should be 20 times more tokens than parameter size for an optimally trained model, I think. And so this is 40 tokens, so they're higher than that, which means that it's trained compute optimal. And these are the flops. So this is how much in a compute it would need. And so this is the 6NP. So we would need 6 times the size of the data sets times the size of the model, which comes out to this number here. In the paper, they say that they trained it on 16,000 GPUs. That's how many H100 NVIDIA GPUs, which have an average throughput. I fixed the error. I fixed the typo, but I left the O, of 400 teraflops. And so that comes to about 70 days. So if you go in and say, okay, well, this is how much compute I need, and this is how much I have, you divide these two numbers, you get about 70 days. In the paper, they say that you used about 30 million GPU hours, which again comes to pretty close to about 70 days to train this model. And so in terms of cost, Jan Dubois has a lot more information about estimates. He's estimating that the salary of these people is about $500,000 and so on, and more information. But he comes up with an estimate that the price tag of this model training is going to be about 65 to $85 million. And the carbon emitted is about 440, I guess that's tera CO2, which is equivalent to about 2,000 return tickets from JFK to London. Okay. And so this shows you that training a model from scratch, which is really, really intense, and it's not for the average individual anymore. So it's now been constrained to companies that have a lot of resources, and they release these models for the general use, either as they can allow you to use it as closed source, as a SaaS solution. So they put an API and they allow you to call that API for cost. Some people like Meta, they release the open weight model. So that means that they release the weights of the models, and so you can play with it and deploy it locally, but they don't release code or information about how it was trained, nor the data set. And then there's open source models, which release everything. So they release the weights, they release the data it was trained on, and the process of which it was trained, so you can reproduce that process. And usually academics go for open source, and so they release everything. They don't have these budgets. I was an academic for a really long time. We don't see these budgets. And so work in academia, interestingly enough, artificial intelligence or machine learning is one of those very few cases where industry has taken over academic, like it has superseded academic research because of small budgets for labs. A lot of what academics do is really focus on algorithms. How do you perfect the algorithm? How do you do smart tricks to be able to do some of these things at a better cost, right? Whereas industry, there's a lot of money, and so they crank up the compute. And so some of the notes is, what is the next model? Well, there's usually a 10x more flops. So the factor of increase from cycle to cycle is roughly 10x. And the complexity of this process, of the training process, grows quadratically with the length of the input sequence. So the more data it sees, then the more it needs a quadratic amount of resources from there. Okay. So again, just to compare predictive ML versus GenAI, the model sizes are very different. Again, in the millions for predictive ML, for GenAI it's the millions of trillions. That means that the data demands are also very different. So you need a lot more data for GenAI than you do for predictive ML. And of course, that means that the training compute is a lot bigger. And so I was able to train predictive ML on my computer. I don't think most of us can train a GenAI model, at least not a serious one. Actually, no, I should say Andrej Karpathy, who is a really big name in machine learning, has written a nano GPT. Again, you can see this in the reference section. A nano GPT, which is a smaller model. It's less than 300 lines of code, so you'll be able to see what it looks like, and you'd be able to run it and train it, I think. So if you're interested, look at that. And so in terms of training, the way that predictive ML is used is usually you customize the model with your own data. But with GenAI, the training is usually done by big providers and released to the public. For use cases, predictive ML is better at very specific tasks, whereas GenAI is capable of general tasks. In terms of cost, predictive ML is cheaper. So cost divides into a lot of things, right? There's the training cost, there's the inference cost, and then there's the total cost of ownership. In terms of training cost, GenAI definitely costs more. In terms of inference, it should definitely cost more because it's a bigger model. But it depends on whether you're using a SaaS solution or you're deploying it yourself. But in general, predictive ML is cheaper. Where it becomes cheaper to use GenAI is if there's not a predictive ML model that's pre-trained, and you have to hire people to train that model and find data and do all of that, and a GenAI model can already do that, you really save that piece. And so when a pre-trained predictive ML model doesn't exist, then a GenAI model can be cheaper because you're saving on setting up that model, if you will. So the difficulty in predictive ML, like I said, is really understanding data and data processing, ML algorithm, ML ops. It's a pretty complex process. The difficulty in GenAI is really about model selection, prompt engineering, evaluation, because they produce open-ended results. In terms of AWS tools, predictive ML, the main service for that is Amazon SageMaker, and for GenAI is Bedrock. Okay. So now choosing GenAI versus predictive ML. The main difference between GenAI and predictive ML, there's a lot of differences, but the main three big ones is really the model training. Usually for GenAI, you can't train the model from scratch just because of the estimates that we just saw. In predictive ML, it's a lot more, it's easier, and so a lot of people do it. In terms of, and often there is a lot of pre-trained models out there, but sometimes for your particular use case, you might have to train your own model. The model sizes and the required resources are just vastly different, like we just saw. And GenAI produces open-ended outputs, which makes them a lot harder to evaluate. What I recommend to people is use GenAI foundational models for general tasks, for quick turnaround. So if you don't have the time to get your data, to train the model, to evaluate it, to deploy it, to run that whole cycle, then a foundational model that is ready to go is a good option. If you don't have the expertise, then something that is pre-done is better. But if you can find a predictive model that's pre-trained, it's going to be cheaper, and I'll show you an example. And if you don't have data, then foundation models are a good idea. You use predictive ML for very specific tasks, tasks that require great accuracy, because you can control accuracy and compliance a lot more with predictive ML than GenAI. If something is a long-term project, the price of a GenAI model will catch up to you. If it's a really long-term project, training your own model in the long run will become worth it. And if the project load is really large, so if you're pinging that model millions of times a day, then again, the costs will catch up to you. And so owning your own model and having a smaller model that's customized for you is definitely a better idea. And if you have high compliance projects, because you have a lot more control potentially over a predictive model than a GenAI model. Okay, so I'm going to give you an idea about the training data. Again, I'm going to go through it fairly fast, but it's good to see. Collecting data is really hard work, and often it's a heavily guarded secret by companies. They don't always tell you what they're doing and how they're doing it for a variety of reasons. I mean, some of it is because they think of it as the secret sauce for from what the model is learning. A lot of it also is because there's compliance and legal issues and patent laws, and it's not really clear what is being collected and how it's being used, which is very unfortunate. But anyway, we don't always have that information. But here's an example of how this process would go about. You would download all of the internet. And so people use web crawlers. You can look at Common Crawl, which indexes the internet. There's currently about 250 billion pages online, which is roughly about 1 petabyte of data. And you extract the text from the HTML. So when you scrape the internet, it's all HTML docs. Of course, you extract the actual text from it. You filter undesired content. You do deduplicate because, of course, a lot of pages are found in different places and several times. You add heuristics to remove low-quality documents. There's some model-based filtering as well, again, to filter out some stuff. And then you classify your documents to be able to decide on how much to use of what, right? You definitely don't want a model that's trained on social media predominantly, right? So understanding what the documents are and what they relate to and so on is important. And then you use that to train your model. Again, this is the devil's in the details, and this is a really high overview. I think probably the data part of ML is usually the longest part of ML. And so this just gives you an idea of the steps, but this is a long and painful process. There's some open source academic data sets if you're interested. There's the C4, the Pile, Dolma, and FineWeb. And if you Google those, you should be able to find them online. And so again, like the bigger the parameter the model is, the more parameters it has, then the more data it needs to see. And today's models are trained on about 15 trillion tokens. So we saw in the Llama 3 model, it was about, I hear 15.6 trillion around. So that's where models are today. In the words of Jan LeCun, it's trained on enough data that it would take you and me 20,000 years to read. So these things chug a lot of data, and they have a lot to learn from. And honestly, the way they work, they can do some wonderful, some really amazing things. But again, they're really big models, and they see a lot of data that you and I can never process in our lifetime. Okay, how to choose an LLM. So one easy way to choose, of course, to constrain your options is looking at the input and output modalities. So different models, there's some models that take input text and output text. There's some models that take text to image, image to text, videos, and so on. And so you need to understand what is going in the model and what is coming out, and that already reduces your pool of models. You want to look at the performance on required tasks. So LLMs have a lot of different capabilities. And so there's a lot of evaluation metrics out there that they're run on. And so there's evaluation data sets that look at reasoning, some that look at coding, some that look at summarization, and so on. And so if you are interested in a coding model, for example, you would want to go and pick a model that does really well on coding evaluation tasks. And the way you do that is you look at the model card. The model card is, you can think of it as the ID of that model. It's the ID card of that model to tell you what that model does, what's the input, what's the output, how it was trained, how big is it, what is it good at, and so on. And so by looking at the model cards, you would be able to potentially choose one. Just as a ballpark for model sizes, a model that is roughly 1 billion parameters is good with pattern matching and basic knowledge of the world. When it gets to the 10 billion, it has greater world knowledge, and it can follow instructions, basic instructions. But when the model gets over 100 billion, then it has rich world knowledge and complex reasoning. So depending on the task you want to do. But again, I think very few, no, we have 70 billion llama models. So you can, depending on what you do, the bigger the model. It's true that the bigger the model, the more tasks it can do, but it also means that the more expensive it is to have and maintain. Then there's the closed source SaaS option versus the open source model option. So SaaS models, again, are easy to use in application because they're calling an API. They're more powerful models because these companies have a lot more money than we do. Not true, actually, with DeepSeek now. But again, closed sources is more likely to because of the money involved. I am a great proponent of open source because with collective knowledge, we can get further. But again, the cost of training is not trivial. In terms of open source, again, you've got full control of the model. You can run it on your own devices. You can have full control of the data privacy, so you're not sending your data outside of your domain. There's a lot of other things you can consider, but these are some of the things that I look at. There is a difference between the predictive ML and the GenAI lifecycle. So in terms of the predictive ML lifecycle, what we do, again, we looked at this, we frame the problem, we source the data, we choose the model, we train it, we test it, we deploy it, and we maintain it. And we looked at this a couple of times now. In terms of the GenAI lifecycle, what you do is you scope your project, you look at your business requirements, then you build the system. So you choose the model, you prompt engineer, you adapt that model to your needs, then you evaluate your performance when you're happy with it, you deploy it, and you monitor it. The main difference really is about this whole sourcing your own data and training, which is not present in GenAI. Again, because of the price tag, maybe one day. So whereas predictive ML, much of the work is about customizing the model to excel at a specific task, GenAI is more about extracting what you need from a general purpose model. So this model knows a lot of things. It knows 20,000 years worth of data, 15 terabytes, trillion tokens, 15 trillion tokens, and you're asking it for maybe what, 100 tokens or 1,000 tokens. So it's really like asking for a needle in a haystack. And so how you frame that question or how you talk to the model would kind of helps your success in getting what you want. And so this is where prompt engineering comes in. Prompts are, again, like we said, the input to that model is your question, is what you are telling the model. So prompt engineering is editing that input or playing with it to drive the desired output from the model. And if we want to think of the prompt, again, this is the input to the model. There's a question there. The most important thing, the required thing is the query, is what is it that you want this model to do, is the question. But then there's a lot of other things that you can add to the context of that prompt. And so you can give it instructions of how to perform the task. You can give it an objective or a mission to achieve. So you can tell it, we are trying to accomplish X. You can give it a persona. You say, okay, well, you are a doctor or you are a lawyer. This changes the lens with which the model gives you the response. You can give it constraints. So you'd say, oh, avoid this or don't do that. You can give it examples of the output. So you demo the output. This is where 0 shot, 1 shot, or few shot learning comes in. So you give it an example and it allows to, it tries to mimic it. You can give it context, so more information. Or you give it tone. You can give it, there's a lot more that you can do. But what I want you to know is that, again, this model is huge. It's seen a lot of information. You're trying to get at a very specific response out of it. And so the more well-formed your prompt is, that the higher your chances of success. And so prompt engineering best practices, give clear instructions, structure your prompts, include examples. So use all of this that is available for you, right? Use instructions, chain of thought really helps. That's when you tell the model to explain how it's done something. Break down complex tasks, prompt iterations, so you keep trying until it works. Okay, where are we at? 34 minutes. Okay, enhancing LLM performance. There's several ways to enhance LLM performance. I've divided them in two main categories. There's weight preserving techniques. This means that the model itself is unchanged. The model weights are the same, but what you do is you focus on how you interact with that model. So an example is prompt engineering. You are changing what input you're giving it, but the model itself is not changed, but that does increase performance. RAG, for example, when you add an external knowledge base as well, that helps the performance of the LLM without changing the LLM itself. There are weight altering techniques, so the model itself changes. And so you're fine-tuning, you're pre-tuning. No, you're not pre-training. This is from scratch. This is too expensive, but you're fine-tuning so that you add a layer. And there are a lot of different techniques like PEFT, parameter efficient fine-tuning, and other ways that have been, and quantization and so on, that have been made to make handling models a lot better. Okay, so there's the weight altering techniques and the weight preserving techniques. The way you should go about it is try the weight preserving techniques first. So do your prompt engineering, then your RAG. If that doesn't work, then you move on. Don't start too complex because it's going to get expensive very fast. Okay, so what is retrieval augmented generation, or RAG? This is a method created by the FAIR team at Meta to enhance the accuracy of an LLM. It improves LLMs by adding the information, by an information retrieval step before generating an answer. And so what we see here is you've got your user, they've got a prompt, this is the question, and you've got an external knowledge base here, and it could be anything. It could be the documents from your company, it could be field-specific information. And information is retrieved from this database. It's used to augment the prompt and then sent to the model. And that kind of helps the model in different ways. And then you get a response. Okay, so this is the simplest. This is a basic vanilla RAG architecture. It's pretty simple. And so the benefits of RAG is it allows you to potentially cite resources because you've got all of this metadata here, data and metadata. You can add up-to-date information beyond the cutoff date of the model itself. You can add domain-specific knowledge of your field. You can add specific knowledge to your company, perhaps. It reduces hallucination because it gives the model more resources, and it improves performance without actually training. The trade-offs, of course, is that it does increase latency. You've added an extra piece of the system, and it increases cost. So you've added this extra system, right? It's cheaper than actually changing the model, but it's not cheaper than just using the prompt engineering, for example. This is a more complex view of this. So when you want to set up a RAG system, there's a few steps you can go through. So these are documents, you can chunk them. You chunk them, which means you cut them into smaller pieces, or you divide them into smaller pieces, and then you embed them, which means you vectorize them. We'll talk a little bit about what embedding and vectorization is in a little bit, but you go through these steps, you chunk, you embed, and then you store it in the database. And then when you want to use the RAG, you query the database, you retrieve the information you want, you add it to the prompt, and then you generate the answers, okay? Now, again, this is an abstract representation of this. The devil is in the details. There are so many decisions to be taken at every step of these. How do you chunk? What metadata do you save? How do you embed? Which embedding model? How are you going to retrieve? Are you going to retrieve based on semantic search, or what function are you looking at similarity at? There's so many details across of this, but my point in putting this series is to really give you an abstract view so that it's not as intimidating as it seems. Okay, GenAI under the hood, concepts that are important in LLM. So the tokenization. Tokenization is the initial phase of interacting with LLMs. What it involves is the breakdown of input text into smaller pieces known as tokens. And we'll talk a little bit more in detail about this. So tokenization is model dependent. Each model ships with its own pre-trained tokenizer and model weights. And embeddings involve transposing the words into mathematical space, and we'll talk a little bit more about this. And the transformer is the model at the heart of the LLM. Again, we're going to have slides to talk more deeply about these. So what is tokenization? Again, it's the process of breaking down the text into smaller units called tokens. The benefits of this is cost efficiency. So the transformer performance, like we said in the last structure, grows quadratically with the terms of the input token. So if we were to tokenize, if we could break words down into letters, that would make the input a lot longer. And so the performance would be terrible, be really expensive. Tokenization reduces the space complexity of words. So when you tokenize, then the space is a lot less. So instead of having all of the conjugation of the words, for example, you would have the base word and then the possible conjugation. So instead of, which reduces the space complexity, you would have less information there. It's really good with things. It's useful because then mistakes, spelling errors, and things like that are not as dramatic to the model. The side effects, of course, is that it creates a lot of weird behavior um, in the model. So LLMs cannot spell words because they don't see letters like we do. They see tokens, and so it doesn't understand the letter layer. They cannot do simple processing, string processing, again, because they don't see letters, they see tokens. They are worse at non-English languages because it's not the same. The tokenization is optimized on the English language, and so other languages might not work as well. It's very bad at simple arithmetic because instead of the tokenizer cuts numbers at different rates, it doesn't see it as the base 10 system that we do. And then it has trouble coding in Python again because of the tokenization of all of the spacing, which some of these have been fixed in various models, but some of the reasons for these is really tokenizations and different, again, like I said, different tokenizers, different models come with different tokenizers, and this website can show you what the tokens look like for different models, and so you can play with that. This is an example of hello there, it's nice to meet you for the tokenizer for Google, Gemma, and GPT-4o, and you can see here that the apostrophe S is treated differently. This is such a small sentence, but you can see that there is a difference. Okay, word embedding or vectorization. So machine learning models are just large statistical calculators. They work with numbers, not with words, right? We as humans communicate with words, but models and math works with numbers. And so we have to convert the words into numbers. And this is what's called embedding or vectorization. So vector embedding, vectorization, embedding are all the same things. It's really a projection of text or images or whatever your input data is into mathematical space, which means numbers. And so, again, this is a numerical representation of non-numeric entities. And there's different examples of how we did this across ages. And so one-hot encoding, for example, if you have an example of that's one way to vectorize a discrete class. TF-IDF, which is term frequency, inverse document frequency, was one way we did it before. Word2Vec is really cool. Here's the paper. So historically, some examples are in the 1954, there was what they called bag of words, which is a simple approach. What it means is they just counted words in a document. So the more if there was more sports words than anything else, then they would categorize it. This was mainly used for classification. They would classify it as a sports document, for example. But that was the simplest way, is how do you take words and get numbers out of them? And counting in the 1954 was the easiest way. And so this was where bag of words come in. In 1972, it became a little bit more sophisticated, where TF-IDF means the term frequency, inverse document frequency. So you counted, but then you divided by how often that term appears in the document. So it's a frequency count. Now it's not a base count or an absolute count. It's a frequency. And then in 2013, Google released the Word2Vec, which was really, really cool, and I think is underlying a lot of the advancement in NLP that we see today. What this is high dimensional vectors encapsulating semantic associations. And again, this I think is one of the flag moments. This is a pivotal moment advancement in NLP. And what it really showed is, so what they did is they took this model, embedding model, they gave it a lot of text data and they trained it. And it came up with these vector embeddings, vector representations in high dimensional space. But then what they showed is that you can do math with words. And so if you said something like king minus man plus woman, the model would give you queen. And so this transformed NLP and modeling on text, because now we understand that we can do that projection really well. And that's the paper, and you can read a little bit more about it. The transformer, this is the last big component I wanted to talk about. The transformer is really the architecture that the model architecture that is at the heart of the LLM. It's the heart of many LLMs. It's a neural network. Again, we played with neural networks, so if you're not familiar, go back to the previous lectures. And it was introduced in a paper, which was called Attention is All You Need in 2017. This was work from researchers from Google and the University of Toronto. It was initially designed for sequence-to-sequence tasks, like translation. I don't know that they knew that it would take the world by storm. This is what it looks like. So again, because these things, the mathematical model tends to be too complex, we visualize them abstractly like this. So this is, you got your inputs. I don't want to go into too much detail, but you've got an encoder, and then you've got a decoder, and then there's a cross attention in between. There's a really good lecture on YouTube, again in the reference, about how this all works, and you can build it from scratch if you want. So look at the references. But what a lot of people in the field did, this started as a translation paper, and then what in 2017, and then what people did after that is they copy pasted the architecture and changed the input. So they changed the embedding, the vectorization, the embedding, and it does wonders. I mean, it's still at the heart of a lot of things we do. There has been some changes to the architecture, very minor from the paper, but again, you can take a look. Before that, the way we did sequences was through RNNs, recurrent neural networks, and their different variations. But those dealt with data sequentially, which meant you couldn't parallelize them. And so RNNs, you could look into them, but the differences that made the transformer the next leap is because it was parallelizable. And so we can train this on distributed compute, and it can get a lot larger. They introduced something called positional encodings, where it doesn't need to retain the sequence anymore. It retains a vector of where every word is, and that helps it not retain sequence, and it helps again in parallelization. And they introduced something called attention heads, which allows the model to assign different weights to different words depending on their context. There is this I wanted to show you. I think this is my last slide. Yeah, okay, so I wanted to show you this. This is a really cool website. Again, you can see it. This is based on the Nano GPT. And what this shows you is this is the embedding. This is the input. Okay, so you've got your data. This is the words. And this is the embedding vector, right? So you've got your tokens. There's tokenization, and data visualization empowers users. So you can see here that empowers has been split into two different tokens. So already this is tokenized, you can see. And this is the positional encoding. So this is the position of each word. And then it's been vectorized. So this is the embedding, the vectorized. So this word has been changed into this vector. And this is using a vector representation that is 768 numbers long. The vectorization changes from company to company and from provider to provider. Google uses a vector that's 768 in length. I think GPTs are closer to the 3,000 mark. The more numbers you have in that vector, then the more dimensionality you are gathering, and so there's more information that you can potentially collect. So just keep that in mind. So this is 768. It's late here. And so now what you see here is this is the information, and it goes through the the layers. This is distributed, so these are different processes happening. And then you can see here there's attention, so it's giving different words, different evaluations or importance, and it goes through the layers. And what ends up happening, what I want to show you is right here. It takes the tokens and then it creates a probability distribution. So this is the probability distribution. And so it says data visualization empowers the users to make, and remember, it's a next word predictor in the sequence. And so this is the possible words that could be next. And it thinks that the next word based on the probability, 28.3, is visualized. So data visualization empowers users to make visualize. Now, again, this is not a great model, and that is the Nano GPT. It's a small model. It's not been trained on a lot of data, but it gives you an example of how this whole thing works. Now, temperature. I didn't talk about temperature and top key and top K. These are hyperparameters that you can, or just variables that you can change that change the model behavior. And what these do is they change the randomness in the model. And so if the temperature is 0, what you can see here it's doing is it's changing the probability distribution at the output layer. And so if this is 0, this model becomes deterministic. It gives the highest, the top word, the highest amount. And so it'll repeatedly do that if you ask it over and over. If you make this highest, then you can see it changes the distribution. There's a lot more randomness. Now the probabilities are very close to each other, and so it will choose one at random different times. So these are what the top P, top K, temperature, they really play at the level of the probabilities. Okay, so that is it for me. These are my references. Jan Dubois' lecture is really good. It goes into what LLMs are, and it is more technical. It is a Stanford lecture in CS, so it goes a little bit more into the weeds if that's what you want, but I personally enjoyed it. There's some lectures here from Andre on, he does a lot about how do you build a GPT, how do you build a tokenizer, how do you do all of these things. Really cool if you're interested in the depth. I personally really like Andrew Ng, and I follow him, and I take a lot of his Coursera courses in deep AI. So these are there for you. And that is it.